What characteristic do you recall from the explanation I just gave? Any characteristic from the damping coefficient? Mrs. Robo, please.
I'm sorry, can you repeat, please? I didn't hear you.
No. I don't repeat questions here. Mr. Iñiguez, please. Mr. Iñiguez, hello. Mr. Iñiguez.
Good afternoon, doctor. I can hear. I don't hear your question. I was in break.
You were not in class. That's the answer. That's the problem. Okay, Mr. Matute. Mr. Matute, can you answer the question? Mr. Matute, please. Mr. Matute, not here. Please, Giovanna, take him out. Mr. Barba, please answer the question. Mr. Barba, please.
Yes, doctor, I'm here. I don't listen to you.
That's the problem. You're not in class. See, everybody has turned off their cameras. Everybody turn on their cameras. Giovanna, if you don't see somebody, take him out of the class. Okay?
Okay.
Do not complain on her. Complain on me. It's a rule from now on. If somebody does not turn on the cameras, take him out, and that's it. Don't doubt. Don't doubt. The problem is with me, not with you. Okay, I have two people that I don't see their faces. Please take them out right now. Okay, I need to remember, what characteristic did you recall from the explanation from damping coefficient? Anything that you remember? Mr. Jimenez. Mr. Jimenez, please. Anything that you remember from the explanation I just gave?
Reduce the velocity for regular motion on this oscillation. Okay,
yeah, velocity is extremely important. When you have no velocity, and you will see the results in a minute. Yes, there is an extreme reduction in damping coefficient. And that's why the IMO includes this condition, dead ship condition, as an extreme situation to analyze the stability of a ship. If you have no velocity, damping coefficient is very small. And if your ship stands that situation, that means that when you have velocity, the damping motion will be reduced. Then you will be okay. Okay. Mr. Galarza, do you remember anything else from this? For example, do you remember the name of the components? The components?
I remember just eddy.
Eddy.
Friction, eddy, and the friction.
Eddy, friction.
Lifting.
Lifting, three.
I don't remember the element.
We are missing two.
Bilge,
yes. And the last one? Wave generation.
Wave.
Please have in mind, okay, you do this and you see the surface is being destructed. Yes, definitely. Okay, so those are the main things that we have to keep in our mind, okay? So we have components, okay? The velocity is very important. Viscosity, we cannot avoid, and that's why we need these results, experimental results. Okay, let's go on. Can you see my full screen, Giovanna?
Yes, I can see.
Okay, so let's go on now. As I said before, we did some experiments, 5 or 6 years ago with engineer Pinto. He works in Asinave. Okay, here you see this name again, Ikeda, Professor Ikeda. Okay, with this group of people, they developed a new formulation. It's similar to the formulation that we had before, okay? But they say it is specifically applicable to the case of cargo ships, conventional cargo ships, okay? Since it was more modern, we thought it was a good idea if we checked if we could apply this to a fishing vessel, Ecuadorian ship lines fishing vessel. So that was our question. How applicable is this? It's like a version of Himeno and Ikera's work, which was developed specifically for conventional cargo ships. How applicable is that to a case of a fishing vessel? So we developed this graduation project. So it's the damping coefficient, experimental, enroll, including velocity of advance in a model of a fishing vessel, Ecuadorian fishing vessel. Okay, so in the lab, for example, it's easy to do a test with no velocity. The great contribution of this work was we wanted to see the influence of the velocity. We have read that the velocity was very important, but we wanted to measure. Okay, so this is the ship. Can you read the name, Miss Freire?
Don Fausto B.
Yeah, Don Fausto 5. Okay, so these are the lines of the ship. It's a ship that Sardine captures, and we had this model because we won in the 2 or 3 years before. We were trying to analyze the possibility of installing a bow bulb. We were not successful in doing that. I mean, we didn't get any specific improvement. But anyway, we had this model. So this is the one that we used. Okay. So as you can see here, it has 2 chines. Okay. You see that the keel is not horizontal, typical of a fishing vessel, right? So this is a big space for the propeller. Okay. These are the main characteristics. Okay. The model was 2 meters long. Okay. Some years ago, we decided that at least our model should be 2 meters long. If you have a smaller model, then there's some strange influences, and it's difficult to do any analysis. Okay, and you see that this block coefficient, sectional coefficient, and that rise angle are the same. Yeah, because those are basically non-dimensional by nature. Okay, all the others we try to extrapolate. Okay, so that was our model. And then first, no velocity. Okay, so we employ a pool, aquaculture area. So they allow us to do this test. So we placed our model 2 meters long, like this, and we make it oscillate, and we record the oscillation. And with the decrement, we were able to calculate many parameters. Okay. We use this device that maybe you recognize from their lab. So putting this up and down, we could change the GM, and changing the GM changes the frequency of oscillation. So we could do tests changing the frequency of oscillation, and we could see the influence of that parameter on the damping coefficient. Okay, and you see here, okay, there is a small weight because before the test, we did some inclining experiment, okay, to determine the GM. So we could change the weight, we could change the GM for every test. Okay, these are the conditions that we analyzed. We did returning to port, departing from port, and in the loaded conditions. Okay, this is the mean draft. In this case, we have the larger displacement, and the idea was to increase. You see from here to there, increase 2 centimeters in mean draft. Okay, on here this is the range of application of the formulation. Let me go back just a second, please. We were trying to apply this formulation for conventional cargo ships to a fishing vessel. Okay, so the problem was that we knew that we couldn't do it directly. So we have to be careful. So we said, we noticed that this is the range of application. Okay, so we are at least B over T, we are fine. This condition, CBO, the applicable region. And here, these three, in the three conditions, it's not applicable. Right? Because usually the cargo ships has no dead rise. Right? So it's basically a rectangle. In the case of the fishing vessel, we have a dead rise angle, and that reduces the sectional coefficient. So in this case, that means that this condition, the third condition, okay, gets its 0.8 basically. So it's the closest to the range of application of this formulation. Okay. And then, as we said, with this device, we changed the position of the centroid. So we use 3 positions of the centroid for each loading condition. And from that point, we could go on and do the tests and get through the logarithmic decrement, we could calculate the damping coefficient. Okay. Down here, you see the GM corresponding to these 3 conditions. Remember the minimum GM value for a general ship? Professor Zambrano, do you remember the minimum GM value for a general ship?
0.2.
No. Manrique, do you remember the common value that we have to have in our mind, in our memory for the GM?
I'm not sure, but I think it's 0.15.
Yes, that's the value. Okay, so that means that in this case, in none of them, this is centimeters. So this is 0.06. So all of these are below the minimum required. But anyway, still, we were able to complete the tests. Okay, the idea here was that we wanted to change the frequency of oscillation. Okay, so in this test, since we had the water was very calm at the beginning, we could control no water coming inside the model, right? So we started with a very large value of rho. So the oscillation, it was nonlinear, okay? So we were able to measure how this coefficient changes with the amplitude of the oscillation. And this is what you're going to see here. Okay, now here, this is a very large value. You see that you have 1, 2, 3, 4, 5, 6, 7, 8 cycles. Now, this is basically the waves reflected from the ends of the pool and started affecting the motion of the vessel. But at least we have 7 or 8 cycles to calculate the response. We noticed that there was some wiggling, so we had to do some softening here. And finally, this is you see that there is some changes here because we wanted to filter this wiggling. And after that, we were able to go on with the calculation of the damping. And these are the results. Here, this is the damping coefficient, and here I have the amplitude. And you see that we started in some cases at 20 degrees. I said, you're like this, 20 degrees, and left it, and it started oscillating. So what Juan did was he get the values of the amplitude 1 cycle at a time. And with the extension from one amplitude to the next one, he was able to calculate for every cycle, the damping coefficient. And that's what we try to summarize with these equations that you see here. And that you see that as you increase the amplitude, you increase the level of damping. Makes sense. Makes sense. Okay. So basically, these values here, where they cross this vertical axis, basically those are the values that we're looking for. Those are the values with very small small angle, right there. These are the results, average results. Okay, and you see here I have B1, B2, B3, because this is not a line. Okay, if we do a linear analysis, then this would be a straight constant line. We have a straight line, we have a slope, which is B2. You see there is some curvature, that's why we have B3 here. So we were able to calculate these three coefficients for every test and then do the average, okay? There you see that we calculated the radius of gyration. This is virtual with respect to the beam. It's about 0.4. It's a value that we should keep in our mind. Remember, this is for efficient vessel, not for any vessel. What else? Then we did some tests with advanced velocity. Okay, so we went to the lake. We did something like this. So we developed this device. We were pulling the model with different velocities. And with these strings and with the pulley, we were able to give them a certain initial heel angle. Left it, and then it started oscillating. And we recorded the oscillation. Okay, for example, in this case, you see that it had 1, 2, 3, 4, and basically here, there is nothing else. So basically these 4 cycles, and that's it. That's a dramatic way of telling you that with velocity, the damping coefficient increases. In the other case, you can identify 7 or 8 cycles. Here, 4, that's it. Because it dies faster, because the damping coefficient has increased. Okay? Keep that in your mind. Okay, and after that, we were able to summarize all of this. These are the conditions again. Okay. Again, we were able to change the GM. These are not exactly the same as before, but in that range, right? And then for each one of these tests, this condition, sorry, we changed the fruit number. So we changed the velocity of the model, right? So these are not very large, they're not very high, but still you can see some influence from the velocity. Again, this condition, the third condition, is the closest to satisfy the CM, midship section coefficient. Okay, and here we have the results. Okay, in this case, we were in the middle of the lake, so we were not feeling safe about the model. So that's why we wanted to include only a small initial amplitude and let it oscillate. Because we were, with the motion, some waves are generated, and we had some problems with water coming into the model. So we just started with a small motion, and that's why we only calculated B1. So that's considering that, assuming that the damping was constant, okay? And again, we were able to calculate the virtual coefficient, virtual radius with respect to the beam, okay? Here we have the results. This is zeta. This remember the z coefficient, non-dimensional coefficient. And for this case, this is the loading condition with 48 kilograms. Let me go back. Okay, 48 kilograms, it's condition here, 1. And we said, let me go back one more, that with condition 1, the midship section coefficient was 0.65, which is very far away from the applicable region for this formulation. Okay, what happens with the other? This is condition 3, which is very close to the applicable region. And you see that our data, our experimental data, are in the range of application of the results. So when we are away, condition 1, we can say that it's very dangerous to apply our formulation, this formulation, to estimate the damping coefficient, because we are far away from the applicability. When we are close in the range of application, we're not inside, because the CM, the minimum CM should be 0.9, but we were with 0.8, wasn't that far away. And you see that in that case, you see that there is some very good relationship between our results and Himeno-Ikeda method. Okay. You also see here just a slight increase. That's in the area, in the range of the, remember this increase in the wave damping coefficient? So the formulation from Ikeda included this increment, and in the experimental result, we were able to capture this little thing. So we were really very happy with these results. And the conclusion is quite easy to say that this formulation, even though it was developed specifically for cargo ships, we can apply it to fishing vessels if the loading conditions take the ship to a situation close to the real, to the range of application of the formulation. Okay. Any questions, people? Any questions about this process? No. Okay.
The ear square, what is the minimal value to the AZ? Because in the table I can see 0.68.
You mean here? Here?
Yeah.
Well, the R square here was how good is the, see,
Is that
exactly. What we did here, more or less, is the following, okay? We had a record. Okay, so we have a record. And so on. Okay, so we take this value and this value, and we can calculate the logarithmic decrement, right? And we have this average amplitude. So in here, we have this value, this average value. So we plot it here. And with these two, the relation between these two, remember, sigma is the log of x1 or x2. With this, we can take a z. And here, basically, we have that value. And then we take this and that. So we have a different amplitude, a different ratio. So we have a smaller amplitude and a different ratio. And we were trying to relate these results with these formulas, okay? And the problem is that you see that there is some variation. So with this coefficient R2 tells us how close we are from the quadratic relationship. And for the first two were acceptable, I would say. For the third one, it was more spread. So probably we need some more precision in our results, or maybe we can do some more tests in order to check our results. That's the meaning of R squared. Okay. We were able to do this because the beginning, the first angle here was very large. So it was about, as I said before, about 20. 20 degrees it's a good angle of inclination. The problem with that was that in the pool, okay, the surface was very flat, close to flat. So we were able to get very close when the water was close to the open deck. And then we lift it and we start oscillation. We couldn't do that in the lake because there was some waviness from the motion of the model, and we could have problems with water coming into the model. That's why in this case, we were able to calculate, you see here, this is the constant, this is the slope, this is a quadratic coefficient. So these coefficients we were able to calculate and compare with the Himeno's formulation. Okay, people, for the next assignment, as I said before, I want you to use the formulation from Bhattacharya, but it's not the original, okay? In Bhattacharya's book, there is a reference. So, but I remember what's the source of this reference, okay? So I want you to look for in Bhattacharya's, and what we're going to do is this, okay? In the lab, we have a small model, okay? It has one single chine. It's like that. Okay. There. Okay. So you're going to use this for your calculations. Okay. So in this case, it's about, I think it's about 45 centimeters long. I will put the dimensions. Okay. And the idea is that you calculate all the parameters. Okay. Here you have we can use a weight, so we can move and we can measure the heel angle. With this, you can calculate the GM. Okay. We can also calculate the wave damping coefficient. And I want you to use this formulation by Himeno. With this, you have to use Himeno's program. I can give it to you. I'm not going to ask you to implement the program. The program is already done. Okay, so you have to use it. So you have to prepare a data file similar to this one here. Since in this case, we have a constant section model, okay? Basically, you need only 3 stations. It's constant, right? We're going to make it float with no trim to avoid any problems. But we need this. That's the damping coefficient because of the generation of waves. That's what you have to calculate, okay? And for that, I want you to use this formulation. So I'm going to give to you the this work by Himeno. You have to see what's the meaning of each one of these parameters. Since we are like this in receiving waves from the side, the velocity is going to be 0. So we are not going to be able to check this value. Okay. And once you calculate this, you can use the same parameter in order to calculate for your shift. Okay, that's comes in 4 weeks. You have to calculate it. Okay, that's 2. On Tuesday, I will explain how to calculate in a very simple, extremely simple way, the excitation. So you have virtual, GM, damping, excitation. You should be able to calculate the response. And then what we have to do is compare with the experimental results. Okay? Okay, I'm going to continue with the evaluation of your problem. And hopefully for tomorrow, I will be able to give you some feedback to you. Okay? Any problem with the coming to the university next Thursday before we break? Who would be able to come next Thursday to the university to do the tests? Would you please raise your hand? Okay, we have at least one person.
Doctor, just a
Yeah.
question. What time will be the test?
We agree with Engineer Isaac. Originally, it would be in the afternoon. But it's not going to be in the same hour as the class. Because at 4, it will be a little bit late. I would suggest to start, let's say, at 2 or 3. 2 would be fine. Everybody okay? Everybody okay?
No, no pasó.
No, ya pasó.
Yeah, yes, it's okay, but
Okay.
the
Yeah, okay.
square continue.
Okay.
E square.
Yeah.
Yes,
on
I know.
Tuesday, yeah. 2 p.m. would be fine. 2 p.m. would be fine, but we have to agree with Engineer Isaac. Okay? Because he's the one who is going to be running the shaker. Okay? Did I answer your concern? I wish I had an accelerometer. So we can register this oscillation. Okay, people, then I'll see you Tuesday. Please, I'm going to post homework either today or tomorrow. Please start it right away. Okay, you have a lot of work in this class and also in ship design. So please, I don't want to hear any crying at the end of the semester. Okay, bye-bye now.
Thank you, Doctor.
You're
Have a good
welcome.
night.
You're welcome.
Thank
You're
you.
welcome.